this set of notes, we're going to continue looking at how to find derivatives, and this will correspond with section 4.10 of the textbook. Specifically, we're going to be looking at derivatives of inverse functions and logarithms in this set of notes. So before we begin, let's first review inverse functions. An inverse function is a function that serves to undo another function. That is, if f of x produces y, then putting y into the inverse of f produces the output x. A function f that has an inverse is called invertible, and the inverse is denoted by this notation right here. So in general, the steps for finding an inverse are as follows. We write out y is equal to f of x, we solve for x, and then we interchange x and y. So to start out with, let's look at an example. We're going to find the inverse of f of x is equal to x squared when x is greater than where x is greater than 0. So let's look at the different steps. So our first step is that we're going to write y equal to f of x. So in this case, we have that y is equal to x squared for x greater than 0. So notice here that since we're only concerned with cases when x is greater than 0, this will also produce y's that are greater than 0. And this is going to be useful here in just a moment. Okay, next, we're going to solve for x. So here, if we're going to solve for x, we could take the square root of both sides. So we have that x is equal to the square root of y. Notice here we do not need the plus or minus in front like we did in the previous section. The reason for that is because we've restricted to x being greater than 0. If we didn't have that restriction, we would need to have a plus or minus sign here out front. Next, we're going to interchange x and y. So interchanging x and y, we'll have that y is equal to the square root of x. So therefore, the inverse function of x is equal to the square root of x. And notice, remember up here we said that when x was greater than 0, we produced y's that were greater than 0. So in this case, for these x's, this will be true when x is greater than 0. Now notice this is not because this x is greater than or 0, it's because when x is greater than or 0, this implies that y is greater than 0. I'm sorry, I keep on saying greater than or equal to, I should just be saying greater than. Alright, let's look at another example. So here we're going to find the inverse of x plus 2 divided by x minus 2, and we're going to follow the exact same steps. So our first step is we're going to write y is equal to f of x. So here we'll have that y is equal to x plus 2 over x minus 2. For our second step, we are going to solve for x. So we'll start by multiplying both sides of the equation by x minus 2. Next, I'm going to multiply through by y. Next, I'm going to move the x terms over to the left-hand side of the equation and all the other terms over to the right-hand side of the equation. So here I'm going to have y times x minus 2 is equal to x. Oh, sorry, let me erase that. I'm going to have x minus y minus x is equal to 2y plus 2. Next, I can factor out an x. And then dividing both sides by y minus 1 and I'm going to pull the 2 out front in the numerator. All right, and so now for step number 3, we're going to interchange x and y. And so we end up with y is equal to 2 times x plus 1 over x minus 1. And then therefore the inverse function is equal to 2x plus 1, x minus 1. So let's look at what this looks like on a graph. So here on this graph, I've got f of x is in red, and the inverse is plotted in blue. And here in green, we have the line y is equal to x. So what the inverse function does is we can think of it as flipping the function over the line y equals x. And so looking at the red line, which is our function, we can imagine if we were to take this and fold it over top of the green line, we would find that this corner here moves over to the blue, and this part of the red line would move up to where this blue is. Down here, when we would make that flip, the red would move to the blue here, and the red would move to the blue here. So we're flipping over that line y equals x, and this is how, when we first described inverse functions up here, and we say that an f of x produces y, then putting y into the inverse of x produces the output x, graphically, that's the same as saying that we are folding the function over the line y is equal to x. So we can find the derivatives of an inverse function, and we can do this one of 2 ways. The first way that we could find the derivative of an inverse function is we could first find the inverse function, like we've done here, and take the derivative, or we could apply this rule right here. And the rule says that if f of x is 1-to-1 and differentiable with inverse here, and the derivative evaluated at the inverse exists, then the inverse is differentiable, and this is what the derivative of that inverse is. Now you might say, well, why do I want to go through all this? Looking at this function, first finding the inverse and then taking the derivative seems much easier. And it very well may be. But often finding inverse functions can be difficult. And the nice part about this derivative is if we're interested in the derivative evaluated at a single point, we can get away from actually finding the inverse. And we'll see how we're going to do that with this example. So here we're going to find the derivative of the inverse of the function we just looked at when x is equal to 3. So we're first going to use this definition, and then we're going to go back and actually take the derivative of the inverse function and see if we get the exact same solution. All right, so starting out here, in order to apply this, we do need to make sure that f of x is 1-to-1 and differentiable. So first, the question is f of x 1-to-1? And so one way to find out if a function is 1-to-1 is to look at the plot and use the horizontal line test. Well, we already have a plot of f of x up here. And so remember that f of x is the one in red. And the horizontal line test says that for any horizontal line that we draw, that horizontal line can only cross the function one time. And notice no matter where I draw that horizontal line, we're only going to touch the function once. And so we do pass the horizontal line test, and the function is 1-to-1. And so to show that, we can just state that f of x is 1-to-1 by the horizontal line test. Now, of course, in order to make this statement, we do have to include that plot, and here we have the plot up here. Okay. Question, is it differentiable? the answer is yes. And we can see that if we apply the quotient rule here, we'll be able to take the derivative. So let's go ahead and do that. So by the quotient rule, the derivative of x, now notice we've got two functions here in the quotient. The first function is x plus 2, and the second one is x minus 2. So we take the derivative of the first function, which is just equal to 1, multiplied by the second function, minus the first function, times the derivative with respect to x of the second function, all divided by the second function squared. And now let's go through and simplify this. Notice we have x minus 2 minus x minus 2 all over x minus 2 squared, which is equal to minus 4 over x minus 2 squared. Right? Now, notice up here, in order to use this definition, or to use this rule, we are going to have to find the inverse evaluated at the point. So in other words, the inverse evaluated at 3, because we're interested when x is equal to 3. Oops. So next, we need f inverse evaluated at 3. So in other words, we need an x so that f of x is equal to 3, by definition of what an inverse is. So to find this, what we can do is we can take our function x plus 2 over x minus 2, and we can set it equal to 3, and then we can find out which x that suggests. So here, multiplying both sides of the equation by x minus 2, we get that. And then multiplying through by 3, we have x plus 2 equals 3x minus 6. So moving the x's over to the left, everything else over to the right, we find that x is equal to 4. All right, so therefore, the inverse evaluated at 3 will be equal to 4. So now we can find the derivative. So the derivative with respect to x of the inverse function evaluated at 3 is equal to 1 divided by the derivative evaluated at the inverse function evaluated at 3. Well, we know that the inverse function evaluated at 3 is equal to 4. So this is 1 over the derivative evaluated at 4. Notice that we have the derivative of f of x right here. So this is going to be equal to 1 over minus 4 over x. We're evaluating at 4. So instead of x, we have 4 minus 2 squared, which is equal to 1 over minus 4 over 4, which is just equal to minus 1. So what we have shown here is that the derivative of the inverse evaluated at 3 is equal to minus 1. So let's go back to our geometric interpretation of the derivative to see what this means. So going back up to our plot, remember in blue, I've erased some of this extra stuff I've got here. In blue, we have the inverse function. And we're looking at the derivative of the inverse function when x is equal to 3. So just kind of roughly drawing, about right here is 3 on the plot. So I'm looking for the slope of the tangent line at this point right here, roughly speaking. So looking at the blue line, if I were to draw the tangent line is going to look something like this. And remember that we found that When we took the derivative of the inverse function at 3, we found that value is -1. In other words, we expect the slope of the tangent line to be equal to -1. And looking at this rough picture here, that looks to be about a line with a slope of -1. So that value goes back, it makes sense with our geometric interpretation of what a derivative is. Now, the other way that we could have went about finding this derivative that I alluded to just a little bit ago is we have the inverse function right here. What were to happen if we just took the derivative of it? So let's see what we would get by doing that. All right, so we're going to take the derivative of f inverse evaluated at 3. Now, one thing that's important to note here is just like what we've done in all the previous sections, we do have to take the derivative before we evaluate it at 3. So here we've got the derivative with respect to x of the inverse function of x using our quotient rule. Well, first, notice we have a 2 that is a constant, so I'm going to pull that out, and then I'm going to apply my quotient rule. So the two functions I'm going to have are x plus 1 in the numerator and x minus 1 in the denominator. Looking first at the derivative of x plus 1, I have that is equal to 1 times the function in the denominator minus the function in the numerator times the derivative of the function in the denominator. And then all of this divided by the function in the denominator squared. So now we're going to go through and we are going to simplify. I'm still going to have my 2 out front. In the numerator I have x minus 1 minus x minus 1 all divided by x minus 1 squared. This is equal to 2 times. Notice the x's cancel, so I have -2 over x minus 1 squared. And then notice that this is equal to -4 over x minus 1 squared. So now I can evaluate this at 3. So therefore, the derivative with respect to x of f inverse of x evaluated at 3 is equal to -4 over 3 minus 1 squared. And notice that's equal to -4 over 4, which is equal to -1. So whether we use this method or this method, we end up with the exact same value. All right, so next we're going to look at derivatives of logarithms. So recall that a function f of x is an exponential function with base a from the previous section if it takes the following form. If x is an element of the real numbers and a is a positive constant other than 1. The logarithmic function is the inverse of the exponential function. So in other words, f inverse of a is equal to log base a evaluated at x. So let's start out by finding the derivative of the inverse of f of x is equal to e to the x. We'll notice here that the inverse function is just going to be the natural log of x. And that's by definition of when we have base e and then natural log. So if we want to find the derivative, in other words, the derivative with respect to x of the natural log of x, notice that the natural log of x is equal to the inverse function of x, so this is the same as the derivative with respect to x of f inverse of x. And then based on what we had on the previous page, this is equal to 1 over the derivative of f evaluated at the inverse of f. All right, so we know when we work with base e that the derivative of f of x is just equal to e to the x. So therefore, the derivative with respect to x of the natural log of x is equal to 1 over, well, we're going to have the derivative, which is e to the x, but we're going to evaluate it at the inverse function, which is the natural log of x. Well, we know that e to the natural log of x is just equal to x, so we end up with 1 over x. So the derivative of the natural log of x is equal to 1 over x. We have that summarized right here. So this is for when we're working with base e, and this is when we're working with any other base. So we're going to look at finding the derivative of the natural log of 3x plus 4. Well, up here we know that the derivative of the natural log when we just have x is equal to 1 over x. Here, instead of x, we have a function of x, so we are going to apply the chain rule. So by the chain rule, the derivative with respect to x is going to be equal to 1 over 3x plus 4. That's applying this rule right here. But we have to multiply by the derivative of the inner function, which in this case is just going to be equal to 3. So we have 3 over 3x plus 4. Let's look at one more example. So in this case, we have the log of 3x cubed minus x plus 2. So notice in this case, we don't have the base e. Here, since we have log, we have base 10. So we're going to need to apply the second rule that's in the box, and we're going to need to apply the chain rule because we don't have x inside the log, but we have a function of x. So by the chain rule, we have the f prime of x is equal to 1 divided by log, actually we're going to do log of 10, because again we have base 10 here, divided by what's inside the log function, 3x cubed minus x plus 2, and again this is coming from this rule right here. But we also need to apply the chain rule because we have a function of x, so now we're going to multiply by the derivative of that function. And we have that the derivative is equal to 9 times x squared minus 1 divided by the log of 10 times 3x cubed minus x plus 2. Your book is full of lots of other good examples. I really recommend giving this chapter a thorough read. And then, of course, if you have any questions, please let me know.